So this is just for fun. I'm never going to ask you to do a problem like this because it's kind of a giant headache, but it's also interesting to see how important and how, helpful a fundamental theorem of calculus really is. So in order to do that, what I'm going to do is show you how we would do this integral without the fundamental theorem of calculus, but just using the definition of the integral, which means that we have to write down this sum and take the limit. So when we've done Riemann sums before, you've been given an n, okay? N equals 4, n equals 6. You set up your partition, you come up with the number, and it is an approximation, right? So if you actually want to get the exact answer, you would have to set up the partition, put it into this, but not with n being a particular number. N is just now n. And then we're going to take the limit as n goes to infinity. Okay? So it gets pretty long and, well, so this is the problem we're looking at. This is this parabola, 4x squared plus x plus 2, which more or less kind of looks like this. It's moved off the side a little bit. And our interval for our definite integral is from -1 to 2. Okay, so it's an area somewhat like this. Okay, and as you know, if you did this with the fundamental theorem of calculus, it's like a two-liner. It's easy, right? So if instead we want to do it with the definition of the integral, what we really have to do, I'm going to ignore the limit for a minute, but I'm going to figure this whole bit out. Okay? So first of all, what's delta x? So our whole interval is from -1 to 2. So delta x was b minus a over n. So 2 minus -1 over n. So delta x is easy to figure out. It's 3 over n. But now what's the next thing to figure out is we have to divide this interval from -1 to 2 into pieces of 3 over n. Okay? So yeah, that's fine. If you think about it though, what we have to do is actually figure out what these xi's are, right? Because we can plug in 3 over n here, but then there's this xi star business thing. We have to plug that into this formula, and so we actually have to know what these xi's are in terms of n and in terms of I, right? Well, I is the integral, right? So you're going to take this guy and you're going to break it up. The first endpoint is going to be x0. The last endpoint is going to be xn, and then we have to have some sort of formula for this partition where there's like n of these, right? And some arbitrary interval in here from xi minus 1 to xi. Okay, so the next thing is we have to come up with what this partition is. Okay, so we just start from the beginning. But we know that each of these are a length of 3 over n because we're counting these out as our delta x, right? So x naught was just the starting point. So for x1, I take my starting point and I add delta x, right? Which is going to be -1 plus 3 over n. So this is going to be my x1. My next one is going to be x2. So I take my x1 and I step another delta x. So this is going to be -1 plus 3 over n is x1. Adding another 3 over n. So I have -1 plus 2 times 3 over n. Okay, x3, I'm going to start with x2 again. Just step another 3 over n. So what's going to happen? I'm going to do this. I'm going to add another 3 over n. So we're going to have -1 plus 3 times 3 over n. I'm running out of space. All right, so, but this is the idea. Notice that I didn't multiply that out just because I'm looking for a pattern. I can multiply it if I want, but then it might be harder to see the pattern. Because if I write it this way, you can already immediately see what's going on here. Remember, these are our xi's. So this index corresponds to the I, right? N, we don't worry about till the very end of the problem, right? Because N we're going to take off to infinity, but at the end. But what we're doing here is we're summing over I being each interval, okay? So if I look at these, this is x1 is going to 1, x2 minus 1 plus 2, x3 minus 1 plus 3 times 3 over n. So you can kind of guess that what we want is xi being minus 1 plus I times 3 over n. You just see that from the pattern. And that makes sense. Now we have to double check that it's right? Because at the end, if we did it right, we should get xn. So let's check. If I put in n for I, do I get what I want? Yes, because the n's cancel out and I get minus 1 plus 3, which is negative 2. So that makes me feel like I did my partition correctly, and in fact that is right. This is the value of xi. Okay, so let me write this stuff up because we're going to need it later. I'm going to need this space. So delta x is 3 over n, and xi is minus 1 plus I times 3 over n. All right, good enough? Okay. What does that tell me? What it tells me, now remember with our partition, we said each ith subinterval was going from xi minus 1 to xi. So now I know that if I want to write that down, I'm going from minus 1 plus I minus 1 3 over n to minus 1 plus I times 3 over n. Okay, so I've got my partition set up. Now all I have to do is plug into here. Okay, so I say all, but like, wait, what? What? Where's, because this one has an xi star, right? But that's, if you remember, that's because it's very general. Whatever my partition is, whatever my subinterval is, right? So this is xi minus 1 and xi. This xi star could be anything. It could be the left endpoint, the right endpoint, the midpoint, whatever I want to choose. So because I like to make things as easy as possible, even like a difficult problem, I'm going to choose the easiest possible thing, right? Which is, well, this one looks like it has less numbers, so I'm going to choose this one. So I'm going to do the right endpoint. So I'm going to choose my right endpoint for this problem. For each xi star, it's going to be the right endpoint xi, and that is going to be this. Now that's just a choice, okay? It's the choice that makes my life a little bit easier. If you like, you could do this problem with the left endpoint, and all of the algebra will look a little bit different, but in the end, when you take the limit, you'll get the same result. Same thing if I took the midpoint or any other point in there. Because remember, as the limit, that all shrinks down because I'm taking that delta x to 0. So it's not going to matter for the final answer, but for the calculations in between, they will all look different depending on which point you choose. Okay. But this is my choice. I already have it up there, so I can erase this. We're just going to know that our xi is going to be our xi star. Okay. So what I'm going to do is I'm actually going to erase this picture too, so I have a little bit more board space, because you'll see once I start putting all these things in here, it just gets really a little messy. So I'm going to just start, and I'm going to ignore the limit until the very end. I'm just going to start, and I'm going to plug into this summation. But every time I write the summation, so I remember what I'm doing. So this is my f of x. And I'm putting in that xi for each x. So that gives me this times minus 1 plus I times 3 over n quantity squared, plus x, which was minus 1 plus I times 3 over n, plus 2. And all of that is multiplied by delta x, which is 3 over n. Okay? Now, not that it's that much easier, but to make my life a little bit easier, because I have to work all this out, I want to be very clear that, as I said before, my summation is over I. So n is constant with respect to this summation. So I can pull out the whole 3 over n because I'm multiplying all of this, and there's no i's in this. What I can't pull out of the summation is the I, because I'm going over I. But the other stuff, the constants and stuff, I can pull it out. So let me write that here. And then I'm just going to start working out this stuff. So it's going to be 4 times, all right, so I square this thing, I got 1 minus 6i over n, right, 2ab, and then plus I squared 9 over n squared, plus minus 1 plus 3i over n, plus 2. Okay, so that wasn't too bad. But now what I want to do is kind of clean it up a little bit and combine my like terms. Okay, so let me do constants first. I have 4 minus 1, so 3 plus 2 is 5, so I've got 5. Now, the ones with an I, I've got minus 24 plus 3 gives me minus 21 I over n. And then this last one is going to be plus 36 I squared over n squared. By the way, you guys, the second time I've made this video. The first time I made this video, I went through the whole thing, 20-minute video, got some crazy wrong answer because I forgot to put this 4 into one of these guys. I don't remember which one it was, but yeah. You gotta be careful with that little stuff, it'll all mess you up. All right, so now what do I do from here? I'm gonna break it up into 3 different things. And, you know what? I'm going to break it up into 3 different things. I'm going to write it up here. So 3 over n times the summation of 5 minus 3 over n times 21 over n. Remember we said we could take out everything but the i's, and then the other one would be 3 over n times 36 over n squared times the summation of I squared. Okay. So now to continue with this, you kind of gotta know what those summations are, and you probably know this one, right? So let's start with that one. You remember, you've seen that. Let me actually write it over here because I want that space. So, what is this? This is just 1 plus 2 plus 3. I'm adding all of those up to n. So this is the sum of the first n natural numbers. And you can prove, or probably have seen before, or proven before, or someone made there's some story about Gauss. Anyway, that's what it is. So, and these are, by the way, in the book, if you ever need them, they're very easy also to look up on the internet. I squared, I cubed. This one I don't remember. I just looked this up. It's n times 2n, but they're in the book. Okay, so that's fine. What about this 5? What is that? That one is sometimes a little bit confusing to people because it's a constant, right? So you kind of want to forget about it. You just want to say it's 5, but I have that summation there, right? So what this means, there's no i's in here, which is what makes it confusing, but I still have to add this expression n times. So what this really means is I'm adding 5 to itself n times. And so that ends up just being 5 then. So if I take those formulas and shove them in here, okay, so the summation becomes 5n. This is n times n plus 1 over 2. And this, oh, it was 30, so this is like 108, right? Over n cubed. And this is n times n plus 1 to n plus 1 over 6. Okay, I think it'd be even easier if I just did 3 times 36, because then I can just get rid of the 6. Okay, well, such is life. So we'll do a little bit of cancellation, do a little bit of simplification here. I get 15 minus 63 n plus 63 over 2n, and then so this would be 18, right? 18 times, okay, let's be careful here. 2n squared plus 3n plus 1 over n squared. Okay, now I take the limit. So how do I take the limit? You guys can remember this. I forget what 18 times 3 is, but I can write this out. But remember, these are, you're looking for like the limit as n goes to infinity. This is just going to be the ratio of the coefficients if it's a if the coefficients are the same, right? If it's n and n squared, right? Here, this is 15 because there's no n. So I take this limit, I get 15 minus 63 halves plus 36. Let's hope it's the right answer this time. 3, 4, 5, 51. So 102 halves minus 63 halves. Yeah. Okay, so 39. That's right. That's actually the right answer. 39 halves is my answer. Yay! So that's the area under the curve. And yes, I can tell you, if you just did that with fundamental theorem calculus, it would have totally been a 2-minute problem. You can just check me, make sure I did this crap right. So I hope you enjoyed that.